Today we're going to talk about how to analyze circuits that are excited at multiple frequencies. The circuit I have on the board here contains two current sources, where our first current source is excited at an angular frequency of 500 radians per second. Our second current source is providing excitation at 800 radians per second, and our voltage source over here is providing excitation at 1000 radians per second. Now these are all sinusoidal excitation functions. And so we can use our steady state sinusoidal analysis techniques in this problem. The issue that we are going to face is determining the impedance of our inductor and our capacitor. Now hopefully you recall that the impedance of an inductor, ZL, is simply J omega times L. And similarly, the impedance of a capacitor, ZC, is 1 divided by J omega C. Well, if we have three different omegas, how do we compensate for that? And the answer is that we're going to have to apply the superposition principle. There's no other way around it, because this inductor cannot have an impedance of three distinct impedance values simultaneously, nor can this capacitor. So, let's work the problem first with IS1 on, IS2 off, and VS off. So our first current source on the left-hand side is going to be on, and all of our other sources are going to be turned off. And we're going to be working this in the frequency domain. So the phasor representation of current source IS1 will be 50 angle 45 degrees milliamps. We have our 73 ohm resistor, because the impedance of a resistance is not frequency dependent. Our current source IS2 will be off, so we're going to replace that with an open circuit. So really I'm just going to take this guy out and then slide this capacitor down. Where the impedance of our capacitor, again, ZC, we'll call it prime, is going to be 1 over J omega C. So that's 1 over J times 500 times 250 times 10 to the minus 6. And I can't do that in my head. J times 500 times so that gives me minus J8. Then I'm going to have my inductor, where ZL prime will be J omega L. So that's J times 500 times 13 times 10 to the minus 3. So that's positive J 6.5. My voltage source is going to be a short circuit, so I'm just going to slide this 10 ohm resistor down into this spot to just make things look a little prettier, in my opinion. And the phasor representation of this current I of t will be a phasor current I that's flowing from the 10 ohm resistor to the 13 millihenry inductor. So this is our phasor current I prime. All right, so we have a current source in parallel with this 73 ohm resistor, in parallel with this branch that would be 10 minus J1.5 if we did all of the combining the reactances bits. So I can do simple current division to find out what I prime is. So I prime will be, I'm going to say negative 50 angle 45 degrees milliamps. And the reason why I say it's negative is because when this current hits this node, it's going to split. Some's going to flow down and some's going to flow to the right. Well, this current I prime is directed to the left through that branch. And so current division would give me the current opposite the direction that I'm actually trying to find it in. So that's where this negative sign comes in. Then I'm going to have my fraction bit here. So let's see, I'm going to have 1 over 73 ohms down here. And then the impedance of this branch, which is 1 over 10 minus J 1.5 ohms. Where I got this, the real part is this 10 ohms, the contribution from the resistor. The imaginary part is just these two summed together. Negative J8 plus J6.5 gives me negative J1.5. So there we go. In my numerator, I will have 1 divided by this 10 minus J1.5 ohms again. And so I'm going to get negative 50 angle 45 times 1 over 73 plus 1 over 10 minus 1.5 I. So I get 43.969 with an angle of negative 133.965 degrees milliamps. And I'm going to write that down over here just to keep track of things. Degrees milliamps. Alrighty. Now we're going to rework the circuit with IS1 off, IS2 will be on, and VS will be off. So with this current source off, that's just going to leave an open circuit. So I'm going to have my 73 ohm resistor. The phasor representation of current IS2 will be 75 angle 0 degrees milliamps. the impedance of my capacitor at a frequency of 800 radians per second will be ZC is equal to 1 over J omega C. It's 1 over J 800, 250 times 10 to the minus 6. Is, excuse me, negative J5 ohms. My inductor, I'm going to have ZL is J omega L. So that's J times omega of 800, 13 times 10 to the minus 3. Is positive J 10.4 ohms. My voltage source is still off, so I'm going to draw my resistor down here to kind of make my circuit a smidge smaller. And my phasor current I of t, I will represent as I double prime flowing from the 10 ohm resistor to the inductor again. All right. So my first inclination when looking at this circuit was to do mesh. But I'm not going to do that because when I was drawing things out, I had a little bit more time to think about things. And I can notice that the 73 ohm resistor and this 10 ohm resistor are in series, and they are in series with this J 10.4 ohm inductor. So this is one branch in parallel with that 75 angle 0 degrees milliamp source. And this is a second branch that's in parallel with that same source. So I can get I double prime by using current division yet again. So I double prime. So the current's going to hit this node. Some of it's going to split and flow up and around and this way. Some of it's going to split and flow down and around this way, which is in the same direction as I double prime, so I'm not going to need a negative sign this time. So I'm going to have 75 angle 0 degrees milliamps. Let's see. 1 over minus J5 ohms plus 1 over 10 plus 73 looks like 83 plus J 10.4. And let's see what we get. So 75 angle 0 83 plus 10.4 J minus J5 dang it, these TI calculators don't like it when you press buttons really fast, so I have to slow down. So I got 4.509 angle negative 93.722 degrees milliamps. So let's come over here and write this down. All right, our last step will be to work it with both current sources off and our voltage source on. So with these current sources off, I'm going to have my 73 ohm resistor. This is an open circuit, so I'm just going to slide that 250 microfarad capacitor down, where, again, ZC will be 1 over J omega C. In this case, omega is 1,000 radians per second, so that's 1 over J 1,000 times 250 times 10 to the minus 6. Which gives me minus J4 ohms of impedance. Here's my inductor, where the impedance of an inductor, J omega L. This one I can do in my head, so it's going to be J times 1,000 times 13 times 10 to the minus 3 is equal to positive J 13 ohms. My 10 ohm resistor. And then the phasor representation of my voltage source is 8 angle positive 90 degrees. Oh, and this is a voltage, so it should have been volts this whole time. I apologize for that. And my current will be I triple prime in this direction. So I have a single loop circuit. I can just use Ohm's law to figure out what that current is. So I triple prime will be my voltage, 8 angle 90 degrees volts, divided by this total series impedance, where I have 10 plus 73 looks like 83, positive 13 minus J4 is plus J9 ohms. And I get 95.824 angle 83.811 degrees milliamps. .824 83.811 degrees milliamps. Alrighty. And my last step is to add everything together. So my question for you guys is, can I simply add these three phasor currents together and get the correct answer? And hopefully you're all screaming at the top of your lungs at your computer, no, you can't do that. The reason we can't do that is because all three of these phasors have suppressed frequencies. These are all representative of different frequency components of this time domain current I of t. So we actually need to convert all of these back into the time domain and then add them together to be able to reconstruct this time domain signal. We cannot simply add the phasors together because it's ignoring the fact that all of those phasors are technically operating at different frequencies. So, I prime of t will be 43.969 cosine 500t minus 133.965 degrees milliamps. I double prime of t will be 4.509 cosine 800t minus 93.722 degrees milliamps, and I triple prime of t will be 95.824 cosine 1000t plus 83.811 degrees milliamps. I of t can be expressed as the sum of I prime of t plus I double prime of t plus I triple prime of t, which would give us 43.969 cosine 500t minus 133.965 degrees plus 4.509 cosine 800t minus 93.722 degrees plus 95.824 cosine 1000t plus 83.811 degrees milliamps. So we have the sum of three sinusoids all operating at different frequencies, so there's no simplifications that can be made here. So this is the correct answer for our problem, assuming I've done all of the prior steps correctly. The methodology that we've employed here using superposition, again, is literally the only way that we can successfully analyze a circuit that is excited at multiple angular frequencies simultaneously. There's no way to say, oh, we can work with these two sources on and this source off. If we have three different frequencies, we're going to have to solve the circuit 3 different times. All right, thank you guys for watching. If you have any questions, feel free to shoot me an email or leave a comment.